Keep the door open.
There you go.
Might as well keep the ventilation.
Okay, so everyone can hear us okay and see everything okay. And without further ado, let's get started. I was a few minutes late. Sorry for the technical hitches. This is the first time we've ever had an in-person philosophical issues in space science seminar. So that's the cause. But it's a huge privilege to have Martin Ward with us, and he's been involved in our philosophy of astrobiology project for a couple of months now, and it's got some a very interesting line of research that she's going to introduce today to us, and this may be followed up by a big conference here at Durham in the summer. So without further ado, I'll pass over to Martin, who's going to talk about directed panspermia, Dorum, Vitae. Please, Martin.
Thank you, Peter. So you can't see me, but hopefully you can hear me. If you can't, please put something in the chat and we'll try and sort it out. But I believe it works. So sorry about the delays. It's technical hitches. It's a pleasure to be here. The first time I've been in front of an audience for several years. Well, I think once I've done it last year, but apart from that. So apologies for any rough edges. This is a good practice to get back into the swing of things. So the name, I'm sure those of you with classical education know, Donum Vitae means the gift of life. And I rather preferred that to directed panspermia. I will explain what that means later on. Many of you already know. Just 1 minute about me, that's all I'm going to do. And that is, I'm the Emeritus Temple Chevalier Professor of Astronomy. The picture there is of me underneath my predecessor's portrait in the Great Hall of the Castle. He was the director of the observatory for about 50 years. I haven't been around as head of things for that long. So that's enough about myself, except to say that my main research area is black holes. And so this is something of a hobby. So I'm really learning many things as I go along, and it's very interdisciplinary, so I have a lot to learn. I'd just like to say one thing, and that is already here written down, but I'm not proposing what you're about to hear as something that we should do. I'm merely raising it as a possibility of something that we could do, we meaning society, space agencies, billionaires, etc. And if we were to do it, how should we attempt to control it? And finally, some of these slides I acknowledge are from Warden, a friend of mine, who is the director of the Breakthrough Starshot initiative, which I'll come on to later. As I said, it's very interdisciplinary. It begins perhaps with what is our place in the universe, a big question. These are all pretty big questions. The history of life on Earth and these various alternatives, which I'm sure you're all familiar with, but just to set the scene. Is life on Earth a singular event? Are we genuinely alone in the universe? Or it may be that life is common, but low-level life, not complex life. It may be that intelligent life, if you want to call it consciousness or not, may be very rare. So we could be alone in that respect. We don't know. Alternatively, life may be extremely common, and so may the intelligence. We don't know that either. And there's an interesting question, which of course doesn't answer the question, where did life come from? It merely, in a sense, kicks the can down the road. Where did life come from? Could it have come from elsewhere? So the origin of life on Earth, which is a whole topic in itself, and I'll just mention this in passing. We don't know how it started. We do imagine that it started with something very simple, as shown here. And those of you that are experts in biology will be very familiar with this concept of how life began, but it doesn't tell us what the initial kickoff was, how it actually got going. It all seems very reasonable once you've got the starting block. And then after that, you could say all the rest is history. Now, panspermia is the transfer of life across, well, space in general. And I want to talk a little bit initially about the transfer of life within our solar system before moving on to the bigger topics of transfer of life beyond the solar system and the big topic, which is, should we attempt to do that? So the intersolar system migration of life is a very simple concept. you have some kind of impact, a comet, an asteroid. We know this happens, just look at the moon. And indeed, even on Earth, if you've been to Arizona, there's the famous meteor crater there. If that happens, then some ejector will be thrown up and can escape from that planet, escape velocity being less than the ejector velocity from the impact. The ejector then, this is not just one blob, it's many blobs, of course, it's just debris from the impact. Will follow some path. Some of it will be captured by classical mechanics, the laws of classical mechanics, by the path or gravitational pull of another planet. And then there could be an impact on that other planet. And we know that this happens because we found meteorites and fragments of rock in Antarctica, basically in Antarctica, because how would you find them if they landed in the jungle mixed up with all the other stuff? You'd never find them. But Antarctica is pristine, so these rocks can be found. And by their composition, we believe they come from Mars. And there was a big hoo-ha about 15 years ago, I don't know the exact time, but many years ago now, where it was thought that some evidence of fossilized worms had been found in one of these so-called Martian meteorites. It turned out to be a false alarm. The evidence was not conclusive, and indeed, it was thought that they could easily be explained by other non-biotic explanations. Those of you that are old enough, like myself, to remember the famous science fiction movie, The Quatermass and the Pit, and those of you that are not old enough, I do recommend a look on YouTube or wherever you can find it these days. Fascinating science fiction story about Martians that come back to Earth. They look very much like locusts. I think that's because the budget of the movie was quite low, and they thought they'd use existing animals. So, are we Martians? Well, there are lots of papers on this, very many indeed, but here's one that was a very good piece of work about the natural transfer of microbes within these fragments of debris from impacts that I described earlier. And what this study suggests, based on evidence, classical mechanics and things, not that we found them, of course, but the possibility is it's very probable that microbes have been carried from the Earth to Mars or vice versa. And those of you that are interested in the origin of life in the solar system, of course, the really interesting result would be if we found life elsewhere in the solar system, for example, on Mars, or even evidence there was once life on Mars, and we could prove that it evolved separately. In other words, its handedness, left-right handedness, was different. That would be a huge, interesting result, because it would then say that life evolved separately within a solar system. Because we haven't discovered that, but that would be one of the things to look for. But as Carl Sagan said, it seems overwhelmingly improbable that microbes have traveled to other star systems simply because of the distances involved and the chances. I mean, as the famous Hitchhiker's Guide to the Galaxy begins, space is big, really big. And if you get bits of random debris thrown out at any old angle, the chances of it being eventually captured by another solar system is incredibly remote. Of course, that doesn't apply if you actually had a directed attempt to send life elsewhere beyond a solar system, which is what I'll come on to. So the question, is there other life in the universe? Is there intelligent life? And finally, can we travel between the stars? We are used in a rather general term, that is humanity and the artifacts of humanity, not necessarily human beings. So briefly then, is there life elsewhere in the universe? Are we alone? Well, I'm only going to mention this briefly because it's a huge topic on its own, and many of you that study this area of work will know this material already. Kepler was a satellite, a space mission, which was designed to, amongst other things, it did many things, but to find planets around other stars by looking for their eclipses. And that's to say, when a small planet crosses a large disk, which would be the star of the host solar system, one cannot resolve the star, one cannot see the disk of the star, but there will be a tiny diminution in the amount of light that comes from the star as the small obscuring disk of the planet moves across it. And indeed, this is the number now of exoplanets that have been found by different techniques. I don't wish to go into all the techniques, but let's just look at the number here. So you can see it's a cumulative number up to 2022. I think we're almost up to date, probably January, maybe a few behind. They're being found all the time. The number is many thousands, probably getting up to 5,000 now. Huge number. Not all of these planets are suitable for life. This is life as we know it, as Scotty famously says in Star Trek. There may be other forms of life, primitive life, that can exist on planets which we, human beings, or anything like human beings, could not exist on. So the types of exoplanet range from gas giants, such as Jupiter, Saturn, Neptune, Uranus. These are rather easy to find because they're big. And not only do they have a larger effect when they pass across the image of their host star by diminishing the amount of light, but also they can cause a gravitational wobble. This is another technique involving spectroscopy, where the center of gravity of the system between the star and the big planet is somewhere between them. And by spectroscopic means, the Doppler effect, you can see the effect of this giant planet. It doesn't work for tiny planets because their effect is so minimal. So terrestrial planets are a minority, there's no question, but they're out there, and there's probably, who knows, maybe if you count the whole of our galaxy, hundreds of millions of Earth-like planets that might be habitable, and by that we generally mean where water can exist. So not too hot and not too cold, hence Goldilocks. Could we find evidence for life on these planets which might be in the habitable zone? That means they're not too hot to fry the life and they're not too cold to freeze the life. It doesn't mean there is life. And there are possibilities, which in fact we've started to explore already, to look at the atmospheres of these planets. It's very, very difficult because you can imagine how much weaker the signal is than the brightness of the star. So what happens is we use the fact that the star light is used to shine through the atmosphere as the planet just approaches first contact as it moves across the surface of the disk of the star. We can then study the atmosphere and see what's in it. And then, of course, it passes the other side and we have another chance. And we haven't yet found what you might call a smoking gun for disequilibrium in the atmosphere, which might be a signature of life, such as ammonia, for example. Water by itself is not the only signature, may be necessary but not sufficient. The reason I show this picture, and perhaps you're familiar with it by now, I don't know how you miss it. The James Webb Space Telescope was launched on Christmas Day, very auspicious, just gone. I'm involved in one of the instrument teams, and this is me standing next to a full-size replica of one of the mirrors that you can see here, the 18 mirrors. If you're a member of the university, or even if you just live in Durham and want to see this full-size replica of the mirror, just pop into the Ogden Centre, the funny wooden building, and you can see it in the foyer. You don't actually need to go in, you can see it there. And that's just a replica of a full-size segment. So the James Webb will, we hope, help us in looking at the atmospheres of these exoplanets around other solar systems. And maybe, if we're very lucky, we may find some disequilibrium. Personally, I think it's unlikely that it will be definitive evidence for life, but it will be interesting to see how many of these planets have at least some form of disequilibrium, even if it's not definitive evidence for life. Even NASA, so you might think of NASA as being a bit boring, but they do have a sense of humor. So NASA produced these posters, which you can download, and that is for the future when there might be tourism to these planets. They always have very boring names, like Kepler, named after the satellite 16b, and you can see here the strap line for going there. Go to Kepler 16b, where your shadow always has company. So this is one with 2 stars. And the other one is an exoplanet without a star, found by means of pulsar evidence. And so this one, the strap line is visit this very long, boring name where the nightlife never ends. Anyway, you can look at some of these on the web if you want to put one on your wall. So to finish off the evidence for suitable habitats of life, there may be 10 billion, as Carl Sagan used to say, I can't do the accent, billions and billions, terrestrial planets in the habitable zone throughout the universe. So a stunning number. And of course, who can say whether we're alone? But it would seem to be an exceptionally extravagant universe if some of these places where life could exist did not have life. Is intelligence a common outcome? As I said at the beginning of the talk, that we don't know. It might be that there's life everywhere, but for some reason, intelligence, consciousness is a very rare thing. We don't know at all. There is a search for intelligent life as opposed to evidence for habitable places, mostly done in the radio. It's not so fashionable these days because it's generally thought that these intelligent aliens wouldn't really be using radio unless they wanted to contact us and beamed a radio message towards us. For their own purposes, it's most unlikely they would use radio. It's so inefficient. There are much better ways to communicate. And just as an aside, by the way, SETI, as you know, stands for Search for Extraterrestrial Intelligence. Some of you will have been to Jodrell Bank. This is now a very old radio telescope built in the 1950s. Actually, it only got finished as a result of Sputnik because their budget was about to be cut. It would never have been built. And then Sputnik was launched and they managed to detect a signal. And the government thought, this is fantastic, we've got to keep it going. So you have to be lucky in astronomy as well as being clever. And just as an aside here, the rise of China, that was a 250-foot telescope. This is the 1,000-foot telescope in, I can't pronounce this. Can you help me with the pronunciation?
I won't be able to.
Okay, I'll have to ask one of my Chinese colleagues to Winslow telescope. Let's give that a try. It's absolutely massive, and so it's much more sensitive. It's used for astronomy, but also it's used as part of SETI as well. So that's the search, and as you of course all know, we have not yet detected any signals. There have been 1 or 2 false alarms, but nobody sensible, let's say, believes that we've detected intelligent life elsewhere in the universe. Now then, the voyage to the stars. This is where I will talk about the Breakthrough Initiative. Some of you know about it. It's funded by Yuri Milner. It's a bald-headed chap here in the background with Stephen Hawking, sadly no longer with us, who was part of this initiative. And as you move along the back row, the person second to the right is Pete Warden, who is the director of the initiative, the Breakthrough Initiative. He used to be the director of NASA Ames, which is one of the NASA facilities. And during that time, he developed an interest in this. Actually, he got on the wrong side of NASA because he had a rather wicked sense of humor. And he used to say, what does NASA stand for? He says it stands for never a straight answer. That didn't go down very well with NASA. Anyway, he's now the director. He was involved in Star Wars in the early days, but now he's moved on to, well, I might say, sort of more pleasant things. And the other person next to him on the extreme right is Harvey Loeb, who again is famous in this area. He has very interesting theories, which we won't go into right now, but one of the most recent ones is that an odd-shaped asteroid that passed through our solar system, Oumuamua, I think is the pronunciation, was not in fact an asteroid, but it was a spaceship. But that's somewhat controversial, as you can imagine. And I think the overwhelming opinion is that it wasn't. But it's always interesting to explore these possibilities. So Pete Warden had friends in high places at one time. We're going back now many years. Obama was welcoming Pete, or Pete was welcoming Obama to NASA Ames. He hasn't had such good relations with Trump, as one doesn't in general. And I think this project now is basically not involving NASA, but involving Yuri Milner, who is funding it. The Starshot Initiative, you don't need to read all these names, but it has some quite interesting people. Lord Martin Rees, the Astronomer Royal, and various other luminaries, and several of them are Nobel laureates. So although the whole Breakthrough Initiative, which is very broad, does contain some fringe ideas and some rather curious people, there are core who are in the management committee who are actually rather sensible people. So the Starshot Initiative then, it's $100 billion for research and engineering over 5 to 7 years. We're now about halfway, slightly more than halfway through it. It probably needs to be renewed. That will be an interesting thing to watch, see if Yuri Milner still has enough interest in this. Of course, for a billionaire, which means many billions, 100 million is not exactly small change, but it's not, it's not a huge amount of their wealth. So let's hope it continues. And the idea is to produce a prototype of a very small spacecraft, which I'll show you in a moment, and to lay a foundation for a launch of this very small spacecraft to Alpha Centauri to attempt to take a photograph of the planet to send it back to Earth. And the key thing here is on a finite timescale. So you see here, I've got a couple of these pictures, one's a blow up. This is the size of the spacecraft. So you might be used to thinking of the space shuttle or indeed these entrepreneur spaceships which have room for tourists to go up. They're pretty big. The space shuttle was the size of a large bus, and the entrepreneur's capsule somewhat smaller, but nevertheless big. Whereas this, the thing that's going to be sent to Alpha Centauri or Proxima Centauri, which is a close companion to Alpha Centauri, is tiny. And everything that it needs is on this minuscule chip. So here's a blow up. It has to have a gyroscope, a magnetometer, solar cells for power, for when it's in deep space, and various other things, an antenna, of course, and a radio transmitter to send the image back. So as an aside, Galileo once thought about this. I'm sorry, this is Kepler, not Galileo. So letter to Galileo from Kepler. Ships or sails built for heavenly winds, some will venture into the great vastness. So that was Kepler's letter to Galileo in 1610. So the solution then that Starshot is proposing is a very low mass for obvious reasons, because that makes the propulsion to push it to a high velocity possible. To leave the engine on Earth, in other words, the push comes from the Earth, not from a thruster on board the spaceship, and to attach the chip to a sail. And in this case, of course, not a sail as we know it in sailing ship, but a sail made out of very thin material that will use the solar wind and the propulsion from lasers to push it to high velocities. Not sure if I showed that, just a picture of a nice sail on Earth. So this is what it would look like in space. It would be many meters across the sail for this particular tiny chip. And you can see here the sail deployed, and the chip at the end of it is absolutely minuscule. It would be pushed by radiation pressure from lasers on the ground. Now there's a huge amount of technological development needed, some of which is being done, and some of which actually is the peace dividend from Star Wars, because those of you who remember Star Wars, the idea was to shoot down the, as it was then, Soviet, maybe it would be Chinese now, whatever, missiles in their phase of re-entering the Earth's atmosphere to blow them up harmlessly, quotes, in the atmosphere. However, that didn't really wash with most people that understood the statistics, because in overkill, you can only die once. And as Martin Rees put it, in science, we progress by trial and error. In the case of Star Wars, there's no trial, only error. So Star Wars kind of diminished in its significance, although there are elements of Star Wars that continue to this day, but the technology has moved on. The reason I say Star Wars is because the idea of directing lasers to a fixed point very, very accurately is part of the technology that was developed for Star Wars. So what we would need for this, this project, Starshot, would be an array of lasers many kilometers across. By the way, I'm not giving you numbers here, like how many gigawatts of power it needs, and the technology. I do have information on that, but I figure now what we're talking about is the principle of the thing. Is it indeed possible, rather than what are the mechanics of doing it? So you would need many square kilometers of these lasers, and you'd need them, of course, to be placed such that you could project the object in the direction of the star. So if you're going to do Alpha Centauri, then you need somewhere in the southern hemisphere or the equator. It's no good putting these things for that particular target, which is the nearest star, in the northern hemisphere. So the plan is to send this tiny probe, shown the solar sail is shown here with this, this cross, that's the sail. You can't see the chip because it's so small behind it, and the red is just a representation of the laser beam. And it is possible by calculations involving classical mechanics, you don't need special relativity here to determine this. The classical mechanics radiation pressure on this can accelerate the probe to 20% the speed of light, which means it gets to Alpha Centauri or Proxima Centauri, actually the favoured star with a series of planets, in about 30 years. Whereas conventional spacecraft takes thousands and thousands of years. And the point of doing this is that if you're going to work on this project, and if you start early enough in your career, then there is a prospect, if this worked, of actually seeing the results. If you started in your 20s, you would see the results because it has to get there and then it has to send the signal back at the speed of light. So another 4 years. So you'd see the results of your efforts in 30, 40 years. And that would be a huge incentive to actually do it, rather than to send something where it would be tens of generations before we got anything back. So all that's just setting the scene now in the last part of the talk, directed panspermia. So the idea of life coming to the Earth from Mars or vice versa is reasonably well established, and it wouldn't be a huge surprise if we found that that had happened. However, the idea of sending life from Earth, which is the directed panspermia, I called it Dorum Vitae because I rather prefer that as a title, the gift of life, than this more usual title, was proposed by the Nobel Prize winner Francis Crick and the chemist Orgel in 1973. And their intention was rather different from what we now think would be possible, because they didn't know about the star shot, the idea of tiny, tiny probes pushed by lasers. They were thinking more of sending life essence in traditional spaceships. So in other words, it wouldn't get there for, as I said, tens of thousands, maybe 100,000 years. Just a word about the date here, which I think is interesting. 1973 is when this seminal paper was first written. So you can see that in 2 years' time, or next year, sorry, we're coming up to the 50th anniversary, which is why I'm hoping that there'll be a conference in Durham on this subject. We were thinking about this year, but what with the new version of COVID, this has kind of set things back rather, and for a high-level workshop / conference, one needs organisation. So we think we'll probably postpone it until next year, which would be great because it'll be 50 years since this seminal paper. So I'll keep you informed on that, and I'm in consultation with the Breakthrough people because they would fund it. As I said, $100 million to Yuri Milner for this Starshot project is not small change, but not much of his money, whereas funding a workshop here in Durham is equivalent to us having a cup of coffee. So I'm hoping that will come off. Why should we do it? So now we come to the questions. Should we do it? What's the point? Well, it all depends, I think, sorry, I've jumped ahead by one. If we would do it, could we prevent it? Is it possible to prevent it? Of course, if it was a space agency, a national agency, then governmental pressure could easily prevent it. That would be easy to do, unless the government actually happened to want to do it for whatever reason. But if a few billionaires or 1 or 2 billionaires wanted to do it, I'm not saying that these people shown here do want to do the particular panspermia towards other solar systems, although we all know what Musk's ambitions are regarding Mars, then that would be difficult to stop, because it would not take more than a few $100 million to do. So the idea then that Crick and Watson had, it wasn't the generation ship, it was a smaller scale version of that. But of course, this is a possible way of spreading our life throughout the universe. But the point about this is it would be fantastically expensive. It would have to be a global project, probably costing trillions of dollars, pounds, whatever, euros, and it would be one-off. And so you wouldn't do loads of them, it just would be non-feasible. So this just doesn't seem a very likely scenario to get the whole world on board to spend this amount of money. So this is why we go back to, if not humans, then what about smaller life forms? So the famous tardigrade, is that how you pronounce it? Tardigrade? Yeah. Is this little bug-like object here, which can survive enormous adverse conditions, environments. But even this really is too big to send on these tiny chips. So we'd have to think about microbes, very small essences of life that could be genetically engineered. And it's a little bit dense, this slide, but let me just spend a moment or two on it. So this is an extract from an interesting paper by Sleater and Smith, Science Progress, relatively recently, 2017. They revisited the Crick and Orgel Icarus paper. That was the journal Icarus. And what they state is that it's now possible to dramatically shrink the payload from what Crick and Ogle suggested. They call it the blunderbuss approach of a biological payload of 1,000 kilograms containing 10 to the power 17 microorganisms. Shrink it down to milligrams of material, which would be tailored by genetic engineering, which of course Crick would know all about, but it was by no means advanced in 1973. It was possible to tune it for the planet to which it was sent. And traveling at 84,000 kilometers an hour, this is for a traditional spacecraft, not the Starshot. Traditional spacecraft would take 54,000 years to reach Proxima Centauri, and more than half a million years to reach some of the nearest stars. So not much interest there. So it would be possible that the contemporary view of what we would do would be based on synthetic DNA that could be tailored for such a mission. And just so we know who we're talking about, the picture below was taken somewhat before their seminal paper. Crick is the guy in the back row with the slightly fuzzy hair, and the person next to him is Orca, taken in 1955. The tie club, I'm sure there's some reason behind calling it the tie club, they're all wearing ties, but we don't really need to know that. So there's a cartoon over here about the sort of thing that might be invoked, a Noah's Ark, where the shot is fired from one civilization to another. Okay. So to revisit this with the Starship concept would be what we might do or could do. And as already said, this would be roughly the size of the chip. And those of you that have an Apple Watch chip, just for comparison, that's how big it would be. I've already mentioned what would be on this chip. But in this case, it wouldn't just be things for maneuvering, gyroscope, cameras, and so on. It would be these tuned DNA for the destination. Before we get to these quotes, and rounding up in the last 10 minutes or so of my talk, we would have to send tens of thousands of these, which may sound crazy, but they're so small, they're incredibly cheap. I mean, 10,000 chips of a mobile phone with the DNA in would not cost very much. And once you've got the lasers, it's just a matter of boosting them with the power. So it would be possible to send 10,000. Why do you need to send 10,000 or whatever number you want to make up? It's because the chances of them actually reaching the planet, given that they can't maneuver, there's no retrojets and things very easily, it's just blind chance. But it's possible from celestial mechanics to work out the chances of one of these many, many thousands of chips being captured by the gravitational pull of the planet that you've sent it towards, the star, with the planets orbiting that star. And so there would be a reasonable chance of it reaching its destination if you launched enough of them. So that's something very different from, say, the Starship, the generation ship concept, where it would just be one of these things. So now, sort of rounding up to the questions which I'd like to have some debate over, is these two quotes. Some of you know where they come from, but those of you who don't, I'll read them out. To think of these stars that you see overhead at night, these vast worlds which we can never reach. I would annex the planets if I could. That's one person. A different person says, if there is life on Mars, then I believe we should do nothing to disturb that life. Mars then belongs to the Martians, even if they are microbes. And there was a debate at the Oxford Union just recently, that is the proposition that we should not colonize Mars by Sean, who I think might be on this call. And I'm pleased to say personally that he won that debate. And I'm not sure it's on YouTube, but I should certainly watch it when it is. So anyway, who did the first quote? I'll give you 10 seconds to think about it, but there are no prizes. It was Cecil Rhodes. And he might have sung along to this, although I just made it wrong. So wider still, yet wider shall our bounds be set. God who made us conscious, let our seed be spread. So I think Rhodes would have obviously been in favor of this wholeheartedly, even if it didn't involve people in red jackets and pith helmets. Sorry, there's something to chat there, but we'll come to that in a minute.
Right, yeah, go ahead.
Okay, so the other quote then, I'm sure you recognize Carl Sagan. Leave Mars to the Martians, I don't think that means we shouldn't explore it. I think it just means that we should not colonize it. I'm sure that's what he had in mind. And however, it may be too late. I don't think Carl Sagan's there. I don't think Elvis is on the moon or Carl is on Mars. But it may be that contamination from Earth of some of the earlier probes, which were not sterilized sufficiently correctly or stringently enough, that we may have infected Mars already. We don't know that, but it's possible. So the questions then I would like us to think about: if we're alone in the universe, should we ensure that life spreads forth, or doesn't it matter? So if something wipes out the Earth, this is somewhat the argument of Musk and Planet B. If something happened to the Earth, we should ensure that civilization stays. But of course, if the disaster was even on a bigger scale and it was a solar system disaster, as indeed will happen in a few billion years, nothing to worry about for us, eventually the sun will become a red giant and will fry the Earth, serious global warming that. It'll strip the atmosphere off and everything will be destroyed. So it's a long way in the future. If that is the case, if life then in our solar system is extinguished, should we think about spreading it forth? Is there a realistic prospect to do this? Well, I think I've attempted to say that there probably is, even though we may be decades away from it. We're probably not centuries away from it if we wish to do so, given the resources and given the billionaires do exist as they wanted to do it. So finally then, and this is sociology, should there be efforts to begin a public debate on the question? Is it in any way like genetic engineering? Probably not, because that affects us directly in principle, but in a sense it is that if we can do it, should we do it? And also related to this point, would there be any public interest, or would it be considered to be just pointless, esoteric, counting angels on a pinhead? I don't know. I'd be interested to know people's views on it. And once again, those of you that may have joined during the course of the talk, I want to say that I'm not proposing that we do it. I'm just saying that it is possible to do, and maybe we should open a debate. Finally, a plug for a lecture I'm giving on the Webb telescope at Newcastle on the 4th of May. I only found out last week that the 4th of May is a very special day. I didn't know this. May the 4th be with you. So I'm not sure if you can watch this virtually, but if you want to, you might be able to book to go to the Lit and Fill. That's in Newcastle by the station. Thank you for your attention.
Thank you. Thanks, Martin. Okay.
Do we have questions?
We've got some